Assalamualaikum warahmatullahi wabarakatuh. So I will explain briefly about our projects. Well, we were given a task to design a 4-stroke crankshaft for 4 cylinders engine, and the engine can produce 100 HP with 4000 RPM. But first and foremost, our team has decided to design a crankshaft for a diesel engine, and so all of the calculation provided by our teams are for diesel engines, but not all the parts of the crankshafts are included in our designs, like crankpin, crankweb, and main journals are included. However, for counterweights, crank nose, and oil passages are not included in our designs. And for the material, we have chosen cast steels as our material for the crankshaft. Thank you.
Now I'm going to discuss with you all about the design of the shaft. In order to find the design of the shaft, we are going to find the bending moment and the twisting moment of the shaft first. Then the final value we will sub into the equation of the equivalent moment. Then when we get the equivalent moment, then we already have a value for the allowable bending strength, that's 75. Then in the end we will get the shaft diameter of 46.26 millimeter. Round off we will get the 46 millimeter. Then the next component we will find the volumetric stress. The reason we find the volumetric stress is to compare with the yield strength of the material of our crankshaft. That is 620 megapascal. Then in the end, the result that we get is 129.91 megapascal for the volumetric stress. So as you can see, the difference is a lot. So that means that our design is very safe for the optimization of our crankshaft. Okay, next I'm going to talk about the overlap of the journal. The formula for the overlap journal is the diameter of the main journal plus the diameter of the crankpin, then minus the stroke divided by 2. The reason to find the overlap of the crankshaft is because if the overlap of the diameter is small, then the stiffness of the crankshaft will be increased and the load bearing will be more. So if the overlap is small, then the width that we design for the crankweb will get in lesser. So that means in order for the optimization of our crankshaft, we must have the overlap.
I will explain about flow of designing our crankshaft. First, we gather the engine configuration data consists of number of cylinder, bolt and stroke, and etc. After that, we gather the engine performance data. We are required to produce a crankshaft for that will produce maximum 100 horsepower at 4000 RPM. So we gather the engine performance data of our engine, and then we calculate the crank at the angle of maximum moment. Then we calculate value of all proportional dimensions for our crankshaft, and finally we find the finite element analysis to prove that our design is safe.
I'll explain about the analysis of our crankshaft design. So firstly, when the crank is at the angle of maximum bending moment, we could calculate the gas load in the piston, which we got was 12.88 kilonewton. So secondly, when the crank is at the angle of maximum twisting moment, we could find the thrust in the connecting rod. So in order to find the thrust in connecting rod, we should find the angle of inclination first. So the angle was 8.24 degrees and the thrust was 13.01 kilonewton. We also calculated the tangential and radial force. And for the design of crankpin, by using the formula length equals to Fp over dc times Pb, the length of crankpin was calculated, which is 31.13 millimeters. So, and also we also analyzed the design of the left and right side of the crank web. where we found the bending stress induced, which is 68.56 Newton per millimeter square. So it can be proved that our design is safe because it is lesser than our allowable stress, which is 75 Newton per millimeter square.
Assalamualaikum warahmatullahi wabarakatuh. My name is Norhaziq bin Ishak, and for my part I will talk about the von Mises stress. The von Mises stress that we calculated is 139.91 MPa. When we compare with the von Mises stress that we analyzed through the FEA, we got 0.03128 MPa when the crank has torque applied and 29.63 MPa when the load is applied. We can clearly see that the von Mises stress from FEA and the theoretical calculation have a huge difference. We figure out that the most possible explanation for this huge difference because when using FEA software like Ansys or Autodesk Inventor, we missed some key parameters that needed to be input into the software for the analysis. When few important parameters have not been input into the system, the software can analyze the extra load, so causing the final result of von Mises stress to be much lower than the theoretical stress. Thank you.
Okay, in conclusion, our crankshaft was created and analyzed using Autodesk Inventor. So the maximum deformation appears to be at the center of the crankshaft, whereas the maximum stress appears to be at the fillets, which is in between the crank journals and also the central point. The edge of the main journal is also a high stress area. The crankshaft deformation was mainly bending deformation under the low frequency, and the maximum deformation was located at the link between the main bearing journal and crank pin and crank cheeks. So these areas are prone to appear the bending fatigue crack. So based on our results, we can predict the possibility of mutual interference between the crankshaft and other parts. Therefore, this result provides a theoretical basis to optimize the design and fatigue life calculation. Thank you.